Okay. All right. So, any questions or comments? Maybe I should announce, just in case there's anyone who doesn't know this yet. So there is a Slack for this course. Let me just get the link. This is the invite link for the Slack. And the first assignment has been distributed through the Slack. The first assignment is I didn't LaTeX the first assignment, but the rest of them are LaTeX. Yeah, to get it, you need to join the Slack. Any questions or problems with that? If you can, turn on your video, because I can't really, it's difficult for me to lecture to a bunch of blank screens. Okay, let me turn on my screen share. All right. So let's start. I basically want to complete the description of the Hamiltonian formalism today, and then later this week we should be able to move to the axioms of quantum mechanics. But I have to make sure that this is done properly. The classical mechanics, I mean, otherwise there's going to be a gap kind of in your understanding of how what the relationship is between the two subjects. So so far we discussed the fact that that we have in the Hamiltonian formalism, we have a phase space. And this phase space is not the usual space that you think of. It's not the usual configuration space, which for a point on a line would just be the line, the position of the point. But it's a doubled space. It's always even dimensional. And on this space, the evolution of the trajectory is a first order problem, meaning that we just need to know the position in order to know the future trajectory. We don't need to know the position and the velocity, in the sense that giving a point in phase space is already telling us that information. And the future progress is determined by a first order equation, a system of first order ODEs. And we saw that that in the case of the harmonic oscillator, this system of ODEs is defining us a vector field on the phase space, and that the integration of this vector field is giving us these integral curves, which are just circles. And so we deduce from this, by projecting the circles down to the x-axis, we get this sinusoidal motion in time for the motion of the mass under the force field of the spring. Okay, So, all right. So as we saw, the evolution of the state is given by a vector field v, which I could write it in this way. I could write it as in terms of the basis vectors, it would look like this. But remember that we're in phase space, so there's double the coordinates. We could say there will be 2n functions now. And this vector field is a vector field on phase space. Okay, and you should have this basic example in mind, x and p, and we have this circular vector field with a fixed point at the origin. So the VI's, these are smooth functions on the phase space, which has coordinates x and p. Okay, so so the evolution of the system is all about this vector field. Okay, and there's something very important about this vector field that we need to discuss. But in order to get to the point, in order to not be confused about this, I want to talk a little bit about vector fields. So about vector fields, okay, we could either think of them. There's two ways of thinking about them. We could either think of it as a vector at each point, which varies smoothly. Right, so at each point of phase space, I give a vector, and that vector changes depending on where we are. Or we could think, instead of thinking of what it looks like at each point, we could think of how does it act on functions. It acts on smooth functions so this is all smooth C infinity functions on phase space. These are real valued functions. Okay, and this vector field acts on these functions by differentiation. Okay, and how does it act? So let's say that V is as above, and F is some function on phase space. Then how does V act on it? Well, it's obvious. I mean, we even used the differentiation notation for the unit vector. So this would mean that we're supposed to differentiate and then multiply by this function. So this will be V1, which I don't have to write. It's a function of x and p, but I don't need to bother writing it. Multiplied by df dx1 plus the next derivative, df by dx2, and so on, all the way down to v2n df dpn. So this vector field just acts on functions by differentiation. Okay, and note, So there's two important things to note. So number one, note that that v is determined by its action on functions. Why? Well, how do I need, if I need to reconstruct v, if I need to, if all I know is how v acts on functions by differentiation, how can I determine v? Well, you see, there's a set of very special functions among all these functions. On the coordinate functions. Okay, so if I act by v on x1, on this coordinate function, what is it going to do? Well, I'm going to get v1 multiplied by dx1 by dx1 plus v2 dx1 by dx2 and so on, and all the way to v to the 2n v2n del x1 del pn. And obviously here x1 partial derivative in the x1 direction is going to give me 1, and all of these are 0 because we're in coordinates. It's like asking what's dy by dx. These are all 0. So all of these go away, and we just get v1. So you can see that in order to determine the coefficient functions, all you need to do is apply the vector field to the coordinate function, and we can obtain the VIs. So in this way, v to x1 up to pn in turn, we reconstruct v. We reconstruct the coefficients of v. Okay. So that means that that justifies this second point of view. So there's you could either think of it as a value at each point, but it's often useful to think of how the vector field acts on all functions, in particular the coordinate functions, but all functions. The second thing is, as an operator on functions, what kind of operator is v? Okay, so we know that v allows you to differentiate a function and get another function. So it's a map from the functions on phase space to functions on phase space. And the question is, what kind of a map is it? What kind of an operator is it? Well, maybe the kind of obvious thing to say is that it's a first order differential operator. I mean, you're taking derivatives. You're taking a single derivative, essentially. You don't see a d squared by dx dy. It's just a first order differential operator. But what we're looking for is an algebraic rule that these operators satisfy. And so when you think about this problem, you have to kind of think about what structure does this space of functions have. So the smooth functions, they form a vector space. You can take two smooth functions and add them, multiply them by scalar. So they form a real vector space, but they also form a ring, a commutative ring, because we can multiply functions. We know we can multiply functions. So this has a multiplication. And the question that you always have whenever you introduce an operator on such a space is, how does the operator interact with the pre-existing structure on that space? So this thing is a vector space, and this differentiation, first of all, it's a linear map, because if I multiply my function by a constant, that constant comes out of the derivatives, and it comes out in front. So this is definitely a linear map, R linear. So that's how it's compatible with the linear vector space structure on this vector space. But this thing has a product, and we need to know how does V affect the product. So if I take the derivative of a product of two functions, well, you learned this as kind of one of the first things you learn about the derivative is that it satisfies the Leibniz rule, or the product rule. And this rule says that you differentiate the first function, you multiply by the second, but you also have the term where the derivative hits the second factor. Okay, so this law is an algebraic condition, and this is these two conditions they define what's called a derivation. On C infinity MR. Okay, and vector fields are in perfect bijection with derivations of C infinity MR. And you could think about this a little bit on your own time, to in case you haven't seen it in another class. But this is basically the algebraic approach to characterizing what it means to define a derivative operator. It turns out that a derivative operator will satisfy this rule, but it turns out that anything that satisfies this rule must be a derivative operator. And if someone handed you a derivation, right, how would you determine which vector field it is? Well, all you would need to do is apply this derivation to the coordinate functions. Okay, and that would give you the vector field corresponding to this algebraic gadget. Okay, so all of this was so far I'm just explaining to you a slightly different point of view on vector fields. Okay, any questions about this before I go on? Feel free to ask. How many people have seen this already, this type of approach? Okay, more or less. Some people have and some people have not. Okay. Okay, now, all right. So now, so we need to come to the point. So there's a main point. There's a specific structure that phase space has that we need to describe now. So, and that is what's called a Poisson bracket. Sometimes it's called a Poisson structure, and sometimes it's called a symplectic structure. On phase space. Yeah, so I need to describe what it is. So, so on the smooth functions on phase space, we have a bracket operation. It has two inputs and has one output. So it takes two functions and it outputs a function. Okay, and It's very simple to describe what this is. So in terms of coordinates. So if I have two functions f and g, then you need to take a bunch of derivatives of these functions and combine them together. And the way the combination works is that you take del f, del pi, del g, del xi multiplied together and sum over I from 1 to n. And then you make it skew symmetric. So you switch f and g. Okay. So this will look strange the first time you encounter it. So it's a bidifferential operator in the sense that it differentiates both f and g. Okay, both of the entries, both of the arguments are differentiated. Okay, and it satisfies certain laws. Okay, so here are the important rules satisfied by Poisson brackets. Okay, so number one, it's bilinear. It's a bilinear operation. So you, in terms of real scalars, and it's skew symmetric. So fg is equal to minus gf. Okay, the second thing is that you see if we, and this is a key point which is going to come across multiple times. So if you fix f and you think of f as being fixed and imagine that you've chosen g, right? Then how does this thing act on g? Well, it basically differentiates it with respect to the xi's and with respect to the pi's. And you could imagine that these functions, these derivatives of f, are kind of like fixed functions. So if you kind of ignore the fact that f, just imagine f was chosen for all time, okay? Then this would just be some function, and this would be some function, and this expression would be basically a vector field acting on g. So what does that mean? That means that with respect to g, it's acting like a vector field, and with respect to f, it's also acting like a vector field. So you could say that it's a double derivation, or it's a derivation of f and of g simultaneously. So the way that you can capture all of that information is to say that it satisfies a Leibniz rule.
Could you zoom out a little bit? Thank you.
So the Leibniz rule would be like this, that if we take the Poisson bracket of f with a product of functions, then with respect to that product, it is a vector field, and so it will satisfy what a vector field satisfies. So it acts on g multiplied by h plus g multiplied by its action on h. So it satisfies this derivation law where v is, I'll just rephrase this in this way. So i.e. v given by f blank is a derivation. And there's nothing special about the second argument because this thing is skew symmetric. So it will also be a derivation in the first argument. by using this skew symmetry law. Okay, and the third condition basically has to do that with, so if you remember, whenever you introduce these operations, for example, a typical one would be like a group operation. So whenever you introduce a group operation, it's kind of like this, that it takes two inputs and gives one output, a group multiplication. And whenever you have a structure like this, which takes two inputs and has one output, there's you can try to apply the operation to itself, in the sense that you could then take a third thing and apply this this bilinear operation, or this binary operation, to the output of its own self. Okay, and there's some rules, like for example the associative law, about how this binary operation behaves on itself, and those are usually important laws which govern various different mathematical structures. So in this case, we would like to do the same thing. We would like to say, what happens if we take the bracket of f and g? That gives a function, and then let's say we take the bracket of that function with some other function. And that's where we get what's called the Jacobi identity. The Jacobi identity says that if we take f and g and then bracket that with a third function, then this would be like acting by f on the action of g on h, but it should be skew symmetric. So it's no surprise that there's this term, g acting on f acting on h. So this is the famous Jacobi identity for Poisson brackets. Okay, so I want to make a bunch of comments about this. This is the definition of a Poisson bracket. A Poisson bracket on a ring or on an algebra is a bilinear skew symmetric binary operation satisfying the Leibniz rule and satisfying the Jacobi identity. So Poisson bracket, it only makes sense to have a Poisson bracket on a ring, like on something that has a product, right? Because we need the ability to implement this Leibniz rule, which involves the product. Okay. Actually, okay, so I want to make a few comments. They're kind of not. It's not clear what order to make them in, but let me just make some remarks. Okay, so the first thing I want to say is that if we just look at 1 and 3, if we ignore the product structure on these functions, the product, and think of it only as a vector space, then property 1 and property 3 still make sense. Okay, so property 1 and 3 say that we have this vector space and we have a bilinear product. So we have a skew symmetric thing, a skew symmetric operation, which takes two vectors and outputs a third. Okay, and that operation satisfies the Jacobi identity. And this is the definition. These define what is known as a Lie algebra. So if I have so this is going to be something that comes up for us a lot. So a Lie algebra is a vector space. Usually it's denoted by a lowercase math fracture letter, usually little g. So it's a vector space little g equipped with a skew symmetric bilinear operation. Usually it's denoted with square brackets, but in the special case that it's Poisson, they become curly. Satisfying the Leibniz rule. Satisfying the Jacobi identity. Okay. So now, because I've just introduced Lie algebra, I cannot really go on unless I kind of explain a little bit about, where. Well, I need to explain that you already know two very famous Lie algebras. So this is just an aside on Lie algebra. Okay, I just want to talk about two examples. So the first example of a Lie algebra, which is known to you already, is the Lie algebra of n by n matrices. So let's take the vector space of n by n matrices. Let's say, let me just do it for the real n by n matrices. Okay. Now we know that n by n matrices have a product. We can take the product of two n by n matrices and get another one, but that product is not a Lie bracket. This is called the Lie bracket because it's not skew symmetric and it doesn't satisfy the Jacobi identity. However, if we define the Lie bracket of two n by n matrices A and B to be not the product of A with B, but the skew symmetrization of that product, meaning this is what we normally call the commutator. It's basically measuring the failure of A and B to commute. Okay, and this is definitely a skew symmetric bilinear operation, which takes two n by n matrices and outputs another n by n matrix. And it also, if we check, let's say AB with C, right? Then, so if you just work this out, you'll get AB minus BA times C minus C times AB minus BA. Okay, and then if you kind of rearrange this this information, so if you do it like this, you take an A out, and there's a BC minus CB. So here I'm using this term right here, but I've introduced a term which is not present, so I need to add it back. And let's see, BC, right? Okay, and then if I continue, there will be a B. I'm skew symmetrizing that expression. And what have I used here? So there's BCA, which does not appear, and CBA, which does appear. So this term occurs here, but I introduced a term which is not present, so I need to get rid of it. BCA. Okay, and then you can see that right away here I have a commutator. This is A, B, C. What's in yellow is equal to this. There's extra terms here which I will now write. So if you there's these extra terms: ACB plus BCA minus BAC minus CAB. And now I'm going to collect these to be exactly B bracket A bracket C. So for example, if I look at this term, BAC, that's going to give me B. So there's a minus BAC minus CA. So that's where my term appears here. And the BCA is right here. Right, and similarly, plus AC minus CA, B. So we see that we've got the ACB and the CAB. So in total, we get this result that it's equal to A bracket B bracket C minus B bracket A bracket C. Okay, sorry to go through this in mind-numbing detail, but the point is that there is a natural skew-symmetric operation on n by n matrices, and if you look at how it acts upon itself, the bracket of the bracket satisfies this condition that A bracket B, it satisfies the Jacobi identity. Okay, so we have one Lie algebra. This Lie algebra is known as little GLN, GLNR. So as opposed to the group of invertible n by n matrices, which has the name big GL n R. Okay. Instead of dwelling on this, I just want to go to the second example, which is going to be the main one I need for right now. Example number 2 is that the vector fields on M themselves form a Lie algebra. And this is not an obvious fact, but it's a very important one. So what do I mean by that? So well, how do we define the Lie bracket of two vector fields? So if V1 and V2 are by the way, the notation for vector fields is like a curly X. These are vector fields on M. Okay, then remember that these vector fields, they are derivations. They act on functions by differentiation. So if we want to define the Lie bracket of two vector fields, we need to, one way to do it would be to explain how does it act on another function. So this is now going to be a vector field. And I'm going to define it by its action on functions. How does it act on the function f? This is in C infinity MR. It acts by first acting by V1, or sorry, first act by V2, and then act by V1 on the resulting derivative, and then skew symmetrize this. Okay. And the cool thing is that this operation actually is a derivation. So check that this operation actually satisfies the Leibniz rule, and therefore it defines a derivation. So given two vector fields, there's a totally natural way to obtain a third one by taking the Lie bracket. This is called the Lie bracket. So the Lie bracket V1, V2 is what we've just defined. Okay, so this is kind of interesting because what it means is that, you know, if you think about what a vector field really is, a vector field is an infinitesimal motion. It's a field of vectors that is giving you the infinitesimal data that, if you integrate it, will give you a motion or a map. And the idea is that infinitesimal symmetries have an operation defined on them where you can combine two and get a third. So this gives an operation on infinitesimal symmetries. Okay, yeah, there's a question, Christopher?
Yeah, doesn't the commutator also satisfy Leibniz rule on the commutator on the n by n matrices?
Well, you can check yeah, I mean, there will be some law governing the action on the product, but that product is not because that product is not commutative. It doesn't satisfy. So I mean, the definition of a Poisson algebra requires that it's a commutative algebra, but and here I'm kind of restricting myself to algebras of functions on a space. So because this is not an algebra of functions on a space, it's not a Poisson structure or a Poisson bracket, but there will be a similar law, you know, governing the behavior with respect to the product, the matrix product.
Okay, so like Lie algebras are always commutative algebras?
No, not at all.
Oh,
Lie algebras do not have a product. They have only the Lie bracket. So you see, it's not a question. The question is not, does the Lie algebra bracket satisfy the Leibniz rule? That is an impossible question because the vector space does not have a product. Like, for example, here, vector fields do not have a product. It does not make sense to take the product of two vector fields. You could try to apply vector fields in succession. You could try to take V1, V2 of f, but this is a second order derivative. This is basically what you're doing here is you're taking first the derivative in the V2 direction and then the derivative in the V1 direction. So that's a second order differential operator, and it will not satisfy the Leibniz rule. The cool thing is that if you take this difference, you take the difference of two second order operators, and what you get is a first order operator, and it is a vector field. So the individual summands, you know, these here, this is not a vector field. This is not a vector field, but the full thing, it is a vector field. Okay.
Okay, yeah, that makes sense. So we want to be closed, like into this operation. So if we had like these second order derivatives, then it wouldn't be closed. At least it wouldn't be a vector field anymore, right? So yeah.
Yes. Now, I just want to make sure that, like here, I mean, the point is that whenever you have, so in this case, in this example, it is possible, we have a pre-existing operation, which is just composition, right? V1 composed with V2 and V2 composed with V1. And that composition law, the vector fields are not closed under that composition. We can use that composition to define this operation, and then this operation, defines a. Then the vector fields are closed under this operation. But in general, what you're really looking to do is you're looking to find a vector space, and you're trying to introduce a bilinear operation out of nowhere, which satisfies the Jacobi identity. And that's how you kind of build Lie algebras. You could even try to build them on by hand. You could try to say, take a two-dimensional vector space and let me take a basis, and then I want to define the Lie bracket of the two basis elements, right? And then you try to see what you could, what the right-hand side could possibly be, assuming that the Jacobi identity holds. So you can try to classify Lie algebras in this way, building yourself up. And we're going to do some of that later on. We're going to understand more about Lie algebras. But okay, so we have these two examples of Lie algebras. Okay, the second remark that I want to make is really about the second law, the Leibniz rule. So we see from 2 that if we fix a function f, okay, so if we fix a function f and we look at how it brackets against everything, right? So we fix f, we look at the operation of bracketing against f, we see that that is a derivation and therefore a vector field. Now here's the key idea, right? This is really the key idea, is that whatever this mechanism is, this Poisson bracket, the key thing that it allows you to do is to transform a function into a vector field. And this vector field, I want to remember, I want to kind of use in the notation, I want to make sure that I don't forget that it involves a function. And so I'll put a v sub f there. And the observation is that if we fix a function f, we get vf a vector field. And this is called the Hamiltonian vector field of the function f. Every function by this mechanism gives rise to a vector field. So let me just spell that out. Let's go to Hamiltonian vector fields. Okay, so we fix a function on the phase space. Okay, then this vector field is defined by this f blank Poisson bracket. And let's work out what this vector field actually looks like. So if I want to write this vector field out, what I should do is apply it to the coordinate functions to figure out what the coefficients of the vector field are. So I'll take the bracket of f with x1, and that's the coefficient of d by dx1. And I take the bracket of f with p, n, and that's the coefficient of d by d pn. And if I look at the expression for this bracket, right, it's basically taking the derivatives of f with respect to p's and x's and then multiplying by the derivative of g like this, right? So if g was x1, then this term would not contribute, and only one of the elements of this sum would contribute, namely the one where we take the derivative with respect to x1. And that would just be 1. So the coefficient would be df by dp1. So this would be df by dp1. That's some function, and that's the coefficient of the first unit vector. Okay, and if I keep doing this, I'm going to get df by dpn, d by dxn, and then I'll continue. And the first one, which involves the p's, I need to take the bracket of f with p1. So if I go back to the expression, if I take, oh wait, sorry, what did I do? Let me do that again. No, that's correct. So I'm looking at d by dp1. That's going to act on p1. So it'll be the bracket of f with p1. So if we look here, the way that this is dg by dp1, that's going to have a minus sign, and it's going to have a coefficient, which is df by dx1. So I'll have here a minus df by dx1, d by dp1, df by dxn, d by dpn. Sorry, I'm using a certain convention where the p's have index down and the x's have index I. The x's have index up and the p's have index down. The reason for that is just because of this sum here. You see that the p's and the x's go together with the same, with the same index.
So all those last terms should have minuses, right? Not just the first one?
Yeah, sorry, yeah. There's a bracket here. So basically this VF, yeah, so you see what's going on is that if you think about it, just if you zoom out a little bit, a function is just a single function of 2n variables. On phase space, it's a single function. But a vector field is a vector valued function, and it has 2n components. So the question is, how do I get a vector valued function from a function? Okay, the answer is you need to take its derivatives with respect to the 2n coordinates, and you put them as the coefficients of your vector field. So this is very similar to something you may have already learned, which is called the gradient. So this is similar but different to, but different from the gradient of f. Okay, in the gradient of f, you would have df by dx1, d by dx1. You would have the same variable here and here, and you would not have a minus. Okay, but in this version, in this Hamiltonian version, it's very important that this particular relationship exists between the function and the vector field. Okay, and so here's the key problem, or the key property of this. Okay, so let's look at the properties of the Hamiltonian vector field VF. It has a couple of really important properties. The first most important one is that if we look at how, so this is a vector field produced by F, right? So we started with a function, we produced a vector field out of it. So that vector field, its job is to differentiate functions. But we already have a function, the function that gave birth to the vector field. So it's natural to try to differentiate the function itself by the vector field that it generated. So I could apply the vector field to f itself. And if I do that, well, you can go through all this. You'll see that you'll get df dp df dx minus df dx df dp. So these terms will cancel with these terms and you'll get 0. But I just want to point out that, remember that vf is just the Poisson bracket applied to f, right? So that means that you're just plugging in f into both entries. And because it's skew symmetric, this is equal to 0. So this is telling us right away that vf, that f is conserved by vf. That, or another way of saying it is that vf is tangent to the level sets of f. Okay, so this is very different from the gradient. Whenever you have, if these are level sets, like f equals 0, f equals 1, so on, f equals -1, suppose, the gradient would be pointing in the direction, that f is increasing or decreasing, whatever, negative gradient descent. This would be the gradient of f. But that's not how this Hamiltonian vector field works. The Hamiltonian vector field is actually tangent. This is the v sub f. It's tangent to the level sets, and it will not change the value of f. So what you see here is that this Poisson bracket, it is able to convert a function into a vector field that preserves that function. And so that function will be a conserved quantity for the flow of the Hamiltonian vector field. For any quantity, so any quantity f of xp is converted to a dynamical system or flow with automatically a conserved quantity. And that conserved quantity is the initial quantity that we started with, okay? And the second, I just want to say one thing before we stop. The second important property is that, so far what do we have? We have phase space, we have the Poisson bracket, and we have a function, the function f. The function f generates a vector field, and the vector field preserves the function. But you may ask whether the vector field preserves the other structure that is hanging around, namely the Poisson bracket itself, right? So every time that you add a layer of structure, you have to check whether it's compatible with the previous structure that you added. So we started with a Poisson bracket, and we picked a function. That function generates a vector field that preserves that function, but what about the Poisson bracket itself? So if I take the Hamiltonian vector field of f and I apply it to the Poisson bracket of g and h, okay, then what is this? This is just f bracket gh. And then I can use the Jacobi identity to expand this out. So this will be fg h plus g f h. If you work it out from the Jacobi identity, it looks like this. And then we can reinterpret this in terms of the vector field. We can write it as the bracket of vf applied to g, bracket with h, plus g bracket vf applied to h. So this law here, where the way that the vector field acts on a Poisson bracket is that it acts on each thing in the bracket. So, in other words, this differentiation acts on G and it acts on H, but that's all. There's no additional term for how it acts on the bracket. So for this reason, we say that VF preserves automatically the bracket. And this would hold true also of its flow. VF and its flow preserves the bracket. Okay, so this is the playground. So I've told you everything that is important about the Hamiltonian formalism. In the Hamiltonian formalism, you have a space, which is the phase space, and that phase space has a very important structure, which is the Poisson bracket. And that Poisson bracket sometimes is called a symplectic structure or a Poisson structure, whatever. This Poisson bracket allows you to take functions and convert them to vector fields, which then preserve the original Poisson bracket and the function that you use to produce the vector field. So it's a very clever gadget. It's like a little mechanical machine which can produce motion with conserved quantities, which doesn't ruin the playground. Okay, this is how the Hamiltonian formalism works. The reason why it's so important to understand this Hamiltonian formalism in this class is that quantum mechanics is modeled exactly on this gadget. So just try to get comfortable with the way the gadget works. Okay, that's it for today. I have office hour, so I'm going to stick around. But if you have to go, make sure that you join the Slack and get your assignment. Okay, you could just free for all questions. Go ahead.
When you first learn about a symplectic manifold that comes equipped with like some two form,
yeah,
can you recover the bracket from the two form? Does that two form actually corresponds to the bracket?
I'm trying to look. Are you? Is your video working?
Let me turn on my camera so you can see a human.
Yeah. Okay.
It might be a mess in my room as well.
You're Romain?
Yeah. Hello.
Okay. Hi. Okay. So so if we look at this bracket expression, okay. When you look at this bracket expression, what you see, so to help answer your question, what I would do is this. So first of all, let's get rid of the let's get rid of the arguments f and g, just to make it a bit clearer what kind of an operation this is. It has two inputs, and those two inputs are placed in these slots. Okay, so if you just look at this right-hand side, what it looks like is kind of familiar, right? This looks like a vector field, and this looks like another vector field. But this does not mean that we are composing the vector fields. We're not differentiating with respect to x and then differentiating that by p. These are two completely separate operators. One of them is acting on f and the other one is acting on the other. So this is not a composition of two vector fields, subtract another composition. This is rather a pair of vector fields which are each acting on their separate arguments.
And do you get some sort of like infinitesimal area by multiplying? Is that the idea?
Well, you could think of it as an infinitesimal area, but what I'm trying to point out is that we have two vectors. Okay, and so if you really wanted to think of this as a geometric object, it would be what's called a bivector. you cannot compose the vectors and somehow get a single operator. It's a combination of two vectors, right, which are considered in their own right. So another way of writing this, an equivalent way of writing this would be like this, that you would have d by d pi tensor product with d by d xi minus the d by d pi. Well, let's see here. I want to make it more clear that f and g go in the first and second. So here, remember, I changed the order. If I wanted it to maintain the kind of reading from left to right order, I would need to switch these. Okay, then it makes more sense not to write the f and g, because we just assume that the first argument goes to the first and the second argument goes to the second. So this is really d by d, d by d xi tensored with d by d pi. So we're going to talk a lot about tensor products later, but basically tensor product means you don't do anything. You don't compose them. It's a formal putting one next to the other. So that's why it's called a bivector. There's a shorthand notation for this skew-symmetric tensor product. It's d by d pi wedge product. Instead of tensor product, it's wedge product, d by d xi, and we take a sum from I is equal to 1 to n. So there's many different ways of thinking of this Poisson bracket. One of them is to think of it this way, as a twofold tensor product of vector fields. It's not made of a single vector field, but rather a bunch of pairs of vector fields like this. Okay, so this is a bivector, and we should say that in terms of the tangent bundle, or in terms of the tangent vectors, it's really inside T tensor T, Tm tensor Tm. I'm not expecting people to know this type of notation, but on the other hand, when you learn about symplectic forms, those are two forms. So sometimes you might learn about something that looks like this: a sum of d pi wedge dxi, I is equal to 1 to n. This is a very similar expression. I have a sum of these tensor products of these things, which are not vector fields, but instead they are one forms or covector fields. Okay, so this would be inside T star M tensor T star M. Okay, so what is the relationship between this bivector and this co-bivector, if you want to think of it, or really it's a two form. You could say that this is a two vector and this is a two form. And the answer is that they are inverse to each other. Omega is inverse. So we could say that the relationship between these two things, this thing and this thing, is that they are inverse of each other. Okay. So what do I mean by that? Well, there's one way to think of it is like this, that you see, the notation is supposed to be suggestive. So from the coordinate system, we produced these objects d by dxi, right? These are the unit vectors in the coordinate direction. Unit vector, and so on. What are these things? These are exactly the dual basis in terms of linear algebra of this basis. So yeah, these are, you should just think that we're in a vector space, that this is a basis. These individual ones, I mean, not the bivectors, but the single vectors, these are a basis for the tangent space. And this is a basis for the dual of the tangent space. Okay, and so you could think that this expression, what does it really do? you could think of it as gobbling up something in the dual. You take something in the dual and you pair it with this element of the vector space, and you get, so, let me write it this way. Suppose that we have a vector space V and we have its dual. And we have a basis E1 up to En, and we have a dual basis E1 up to En, such that Ei of Ej is equal to delta Ij. So this is just what we mean by a dual basis for a vector space and its dual. Okay, so if I take, if I produce a bivector, if I take something like, or a two form, let's say I take Ei tensored Ej. Okay, so this is a tensor product of two basis elements of V star, but I can think of it as a map. I can take any vector V, I can write it as a sum of Vi Ei, and I can map this by saying that I want this second element, or maybe this first element, to gobble up this thing and spit out a number. So it will be Ei of V. That's going to be a number. Okay, and I just multiply that by Ej. So this will define a map from V to V star. It takes V to what? Well, Ei is going to gobble up and it's going to give me Vi, and then I multiply that by Ej. That's what this bivector can be thought of. It can be thought of as a map from V to V star. Okay, and similarly, in exactly the same way, a bivector of the form E lower I tensor lower j, okay, can be thought of as taking a dual vector, Xi, which is a sum of Xi Ei, and I can do exactly the same thing. I can gobble it up with the first element of the bivector. I can say Xi of Ei, that's going to be a number multiplied by Ej. And this will be the opposite way. It will go from V star to V. So all I'm saying is that whenever you take two covectors and tensor them together, you can think of that as a map from V to V star. And whenever you take two vectors and combine them together, you can think of that as a map from in the opposite direction, from V star to V. Okay, so so to conclude this thing that I should probably not even be telling you, this two form defines a map from the tangent to the dual of the tangent, and the bivector, which is the Poisson bracket, sometimes it's called pi, goes from T star M to Tm. And the point is that these are exactly inverse maps of each other. Okay, the reason that I introduced the Poisson bracket instead of the symplectic form is that the Poisson bracket is the one that's more useful. It gives you a mechanism for taking a function and converting it into a vector field, right? That's why I want the map that goes from T star to T. I want a vector field at the end. So I want to use the Poisson structure. Otherwise, I would have to use the symplectic form and explain how to invert it and so on. It's just easier to just go directly to the Poisson bracket. Yeah, sorry.
That was very clear. Thank you.
That's way too much information for most people, but hopefully, if you've seen this before, it helps. And if someone wants to ask a really much more basic question, please do. Don't try to limit yourself to these more advanced questions.
If no one else has a question, I have other things, but I really want to give a chance, I guess.
Go ahead.
other questions.
Go ahead. We still have plenty of time.
But it's on the same level, so I don't know if it's interesting
Go
to
ahead.
other people.
Go ahead.
So a symplectic form can always be written in local coordinates as you did. That's some theorem somewhere.
Mm-hmm.
Is the same true of the Poisson bracket? Surely, right?
Like I said before, the Poisson bracket is equivalent information. It's the same information.
Yeah. So you can always write it as in some coordinate system locally dpi dx minus dxi dpi.
If you have the right coordinates,
Okay.
then it looks like this. So in the first assignment, there's some discussion of changes of coordinates.
And this is precisely because of the inverse correspondence between the two.
Yeah, I mean, you could prove it either for Poisson brackets or for symplectic forms, and if you prove it for one, it implies it for the other. Yeah, they're just the same. The other interesting thing is that, you know, I mean, one of the axioms of symplectic structure is that this map should be invertible. So if it's, you know, it's because of the fact that we're requiring symplectic forms to be invertible that we can always invert them and produce a Poisson bracket. But the truth of the matter is that there are Poisson brackets that occur in practice which are not invertible and which are not related to a symplectic form. That's why Poisson geometry is its own topic, separate from symplectic geometry. The Hamiltonian formalism makes sense for any Poisson structure, for any Poisson bracket. So there's many instances where there's Poisson bracket, but we're not on a symplectic manifold, and so it's slightly more general than the symplectic point of view. But
just a basic question: what do you mean by invertible here?
Well, you see, remember how I was saying that
oh, as in from a Poisson bracket, you may get a map into the dual which isn't invertible.
Yeah. So whenever you take vectors and you combine them in this way, 2 by 2, that combination defines a map from the vector space from the vector space dual to the vector space, right? Any kind of bilinear combination of vectors or covectors, whenever you have two together, they define maps. And this is the linear map that I'm talking about being invertible. If it's invertible, then it goes from V to V star. And so that's a relationship between the Poisson structure is one thing like this, right? The Poisson structure is made of two vectors together, and the symplectic form is made of two covectors together. And so they each define maps. I'm just saying that they are inverse maps. It's a map at every point of the manifold. At every point, there's a tangent space, which is a finite dimensional vector space, and there's a dual of that vector space. And the map that I'm talking about is between the tangent and the cotangent space at each point. The thing is, I know that I'm not assuming that the class has a knowledge of these differential geometry stuff. I'm just mentioning it in a kind of I'm trying to discuss the basics because it's very helpful to have the basics in mind when you're doing the quantum mechanics, and I think it's good to start off by assuming that every Poisson structure is of this standard form. It has this very nice form if you use the x and p variables. Anyway, yeah, we'll see some examples this week, and hopefully it'll become a bit more clear. Yeah, vector fields, Poisson brackets, Lie algebras. And the basic mechanism of Hamiltonian mechanics. Yeah.
I have an administrative question, if that's all right.
Yeah, go ahead.
Would it be? I'm not sure if this has been asked before, but would it be all right if the chat log gets saved as well afterwards, in case there's like interesting questions that are So the bottom set is broken up.
Let me just see what the chat log has in it. It's a pain to keep that because I have no place to actually save the Zoom material. I'm just streaming it to YouTube. If you want to go and get the video, they're going to be available on YouTube. Yeah, let me just leave it at that. You can chat away and it won't be recorded for all time.
Okay.
You can say you can ask embarrassing questions in the chat log. How about that?
Question.
Yeah, go ahead.
Could you explain?
Bernie, should I call you Bernie or Poe?
Whatever you like.
It's up to you. It's whatever you like.
Yeah, I like Bernie better.
Okay.
So could you explain, maybe geometrically or maybe just intuitively, how the Hamiltonian vector field corresponds to the tangent of the level sets?
Okay, yeah. So it's not the most obvious thing, because the way that I've presented the Poisson bracket is kind of like a formula. I'm kind of giving you a kind of ad hoc formula for what this Poisson bracket is. But I think, okay, for the first draft of the answer, right? You just need to understand the mechanics of the thing, the way the algebra works out. So from that point of view, the fact that the fact that the bracket is skew symmetric means that f bracket f is 0 for all f. Okay, and what this means is that the way that f acts on f, the way that the vector field flows, is that it does not it just gives 0. So this is like saying that f is constant along the vector field. The partial derivative of f, this equation is basically saying that the partial derivative of f in the direction of the vector field f is 0. And that means that whatever direction the vector field is pointing in, the value of f must be constant along that direction. And that's the reason why it must be tangent to the level sets, because the level sets are where the function remains constant. Right? So this equation is exactly saying that the vector field is tangent to the level set. Okay, so the thing that's maybe not so obvious is why is it that the Poisson bracket has this behavior? Why is it that the Poisson bracket converts a function into a vector field which is tangent to the level sets of that function? Why? And that, that is, there's no real way for me to answer that in a totally honest way, because it's a new structure that you haven't seen before, this Poisson bracket. This Poisson bracket is a new type of structure which exactly does this. That's what it does. That's its main feature. Okay, but what I could say, what I could suggest is this, that you already know about the gradient of a function. So the gradient does not have this behavior. It's exactly opposite, that the gradient points in a direction that the function changes the most, right? Whereas this one, what it's basically doing is it's taking the gradient and it's rotating it by 90 degrees in a certain direction. And because of that, it's taking something which is pointing towards the increasing direction of f, and it's rotating it to make it so that it's actually tangent to the level set. This is not very precise as an answer, because I'm not telling you in what direction exactly is the thing rotating. Okay, and but there is a way of thinking that is like that, where you can say that it's not the gradient, but it's obtained from the gradient by some kind of rotation, which is somehow specified by this Poisson bracket. But I should point out, like, the reason that I don't like that explanation about the gradient is because if I give you a function on a space, it will not have a gradient in general, because in order to have a gradient, you need to have a notion of distance, or a notion of a Euclidean inner product. If you look at the definition of the gradient, you're making use of the inner product on Euclidean space, a notion of distance, or the dot product. And in this formalism, when we're working on the phase space, we don't have a dot product, we don't have a gradient, we don't have a notion of distance. All that we have is this weird Poisson bracket, which is a new type of structure, and it's if I had to draw a picture of what a Poisson bracket looks like, it would be, I don't really know what the best way of drawing it or visualizing it is, but yeah, you will get an intuition for it if you work with it a little bit.
So it's like you take what you know about Rn and then sort of take the properties and then just generalize it using what you see in words. Is that what's going on?
Well, what I would say is that this Hamiltonian formalism, this Poisson bracket thing, it isn't really something that you've seen before usually. I mean, it's a new type of structure which has its own nature. You've probably, like in multivariable calculus or in in multivariable calculus, the types of things that you usually do is you kind of define integration. So you integrate over volumes. So you have a notion of volume. You might have a notion of path length, and so you have a notion of length which uses the dot product, right? If you have the div, grad, and curl and all those operations. But this is a new type of operation. This operation doesn't exist on Euclidean space. It exists on the phase space of Euclidean space. So in order to have this operation, okay, what you need, so the assignment goes into detail a little bit about exactly this point, but let me just say a few words. So to have a Poisson bracket like this, we need we need a space in which half of the coordinates are dual to the other half. So to give an example, what you could do is take Rn and you could take the dual of Rn and take their product together. And you could let the coordinates here be x. I'll put them up, x1 up to xn, and let the coordinates here be p. Okay, and what I mean here is that these are dual. If you could think of them as bases and dual bases. Okay, so the choice of the x's, the choice of exactly what my coordinates are, if you rotate them around, let's say, you're going to get a choice of coordinates. That's like a choice of bases for the vector space. And that choice of basis determines a choice of dual basis. So if I change the x's, I will have to change the p's via dual basis transformation. And it's exactly in this scenario where you have this expression d by dx, d by d pi tensor d by d xi minus d by d xi tensor d by d pi, sum of this. So it's because of the fact that half of the coordinates are dual to the other half that allows us to produce this operation. Because you see, I need to know what's the partner of the d by d pi. I need to know that there is a specific vector which is the partner of this one that they're going to occur together. And that pairing, where they pair off, d by dp1 pairs off with d by dx1, and so on, right? That is because of a duality of the vector spaces underlying them. And this is what is going on, is that this is supposed to be like the coordinates of the the original configuration space. And this is the additional momentum variables which we got from the configuration space. Remember, we said that we wanted to define the PIs to be kind of like the xi dot. In a sense, we want them to be the velocities or the momenta. And so we know that the momenta are related to the original coordinates, and they're related in this dual fashion. Okay, so it's because of this dual relationship that allows us to write this expression. So this is what I mean. It's like you haven't in the past. You probably have not done this before, where you take a vector space and you take its dual and you put them together. You take the product of them, the Cartesian product. You produce a larger space, which is really the product of a vector space and its dual. But when you do that, you get a new type of structure which pairs them together in this way, and that's the Poisson bracket. And it allows you to do this very nice mechanism where a function on this space gets transformed into a dynamical system, which preserves the bracket as well as the function itself. So it's a kind of interesting mechanism that people discovered for doing mechanics, and it's way simpler than, let's say, there's another theory of mechanics which is called Lagrangian mechanics, and Lagrangian mechanics is relatively complicated in comparison with Hamiltonian mechanics. Hamiltonian mechanics is like it's in many ways it's kind of like cheating. It's so simple, right? That all of classical physics is basically reduced to finding the right function on the right phase space, and then once you know that function, you're done. It just generates the motion. So you'll hear a lot of discussion about whether a dynamical system, like a dynamical system, just means that you have some kind of a space and the points are moving, right? I just mean it in a very informal way. That there's a lot of people who study dynamical systems, right? That you invent some kind of a mechanism by which a point on a space moves, and you try to study how it moves for as time progresses. And people who study dynamical systems, they are very interested in the question of whether a dynamical system can be written in Hamiltonian form, meaning, is there a phase space and a function which generates this dynamical system? And the amazing thing is that classical mechanics can be put into this formalism.
Sorry, just to confirm, the P1 and so on till Pn, they are the coefficients of the one forms, right? dx1, dx2, dxn, or do I have the wrong picture?
Yes. So if you have local coordinates x1 up to xn, this will give local basis. This will give a basis d by dx1, d by dxn for the tangent space to a point of the space. well, let me just call it X, the space. But it will also give a basis, a dual basis, dx1, dxn. These are the notations used for the dual basis and the basis. And so a general point in T star XX is a combination of the bases. Okay, so you could take an arbitrary linear combination of the basis elements, and we get an arbitrary element in the dual space of the tangent space at X. And these things, these are the coordinates on the space of covectors. This is a covector. And so if I, to specify a single covector at a single point, we need, first of all, we need x1 up to xn to know where the point is. And we need to know p1 up to pn to know which covector. Okay, and in total, these are the coordinates on the phase space. Okay, so to summarize what I've said on this page, I would say that the phase space is the set of all covectors on X. And that set of all covectors on X, this has a name, it's called T star X. So T star X, you could think of it like this, that we have, if this is X, then we have T star X, which in order to have a point on T star X, you need to know which point of X you're on. And then for that point, there's a whole tangent space, or the dual of the tangent space. This is a point X. This is the tangent space at the point X, which I'm, instead of drawing it as being actually geometrically tangent, I'm just trying to draw it vertically to make more space. And this is really the dual space of that vector space. And in order to specify a point in here, this has coordinates X and P. So P is like that. So basically the idea of the phase space is that we're taking the configuration space, which is just the X's, and we're doubling the variables to include the P's, and the P's are going off in some other direction, which I drew vertically here. And what they are parametrizing is the different covectors to the different points of X. So you could think that the Hamiltonian formalism is really giving a vector field on this big space. For any function, we get a vector field on this big space. And if we study the motion in this larger space, then we can figure out the original motion just by projecting down to X, forgetting the P's.
Just to touch on the Lagrangian mechanics again, we just started doing that on our physics course.
Yes.
But I understand most of it is just variational calculus. But is there any geometric structure, like some geometry related to that, or no?
Of course. The fundamental difference between Lagrangian mechanics and Hamiltonian mechanics is that Lagrangian mechanics is happening on the tangent spaces, not on the cotangent spaces. So it's a and it also depends on having a slightly more data. You need for Lagrangian mechanics, you roughly, well, so you see, like when you construct the phase space, you have this natural Poisson bracket, and the Poisson bracket kind of guides everything. Once you know the Poisson bracket, then you can do this mechanism where a function converts to a vector field, and then you just flow the vector field and you solve the problem. In the Lagrangian mechanics, it is similar in the sense that you have to choose a function, and the function will generate some kind of a motion, but the process is quite different. As you said, the way that it's usually described is in terms of variational calculus, but you could also describe it in the similar way that I did this in producing a vector field. And the truth of the matter is that Lagrangian mechanics and Hamiltonian mechanics are not equivalent. But in an important special case, namely when the kinetic energy is non-degenerate, they become equivalent. They become equivalent through the use of this thing, which is called the Legendre transform. But yeah, so in that case, like there is a large domain of intersection where they are really the same theory, and yeah. So, but actually, we're not going to study the Lagrangian formulation of quantum mechanics. It's not as important as the Hamiltonian one, so we need to do the Hamiltonian one. But all these theories are geometric. I mean, they are all, classical mechanics it has a pure geometric formulation in all cases.
Thank you.
You're welcome.
So if I want to answer myself, the keyword to look up is Poisson geometry, you said?
If you wanted to learn about what? About which part?
If I want to answer my original questions about the tangent vectors and stuff, how that's related to the Hamiltonian vector field.
But which part exactly? The part where I'm talking about?
No, originally I asked how exactly does Hamiltonian vector field correspond to the tangent vectors of the level sets of the function. And you told me that there's a whole theory behind this.
Well, just to make sure that you understand what I'm saying, that if you take a function, that function will have level sets.
Yeah.
The function, if you're on a Poisson manifold, it will generate a Hamiltonian vector field. Mm-hmm. And that Hamiltonian vector field is tangent to the level sets. That's the basic statement.
Yeah.
Right? Okay. So, so the argument for that is what I gave, right?
Yeah.
So that is proving to you that the function is tangent to the level sets. That the vector field is tangent to the level sets of the function. So I think that the main question that you might have is like, how did we come up with this Poisson bracket in the first place?
Yeah, that was your second answer, right?
Yeah. Yeah.
And
so, I mean, you could of course look up Poisson bracket and try to, or you could even look up Hamiltonian formalism. The Hamiltonian formalism is just this, what we're talking about. But if you look at the homework, you're going to be well on your way to understanding the Hamiltonian formalism.
All right. And you also said that variational calculus is the background, the playground of Lagrangian mechanics.
Well, I wouldn't say that. It's more that the typical way that, one way of formulating Lagrangian or Hamiltonian mechanics is as a variational calculus problem. Like anytime that you have a differential equation that governs the future behavior of a particle, you can try to rewrite that equation as being the stationary points of some functional. So you could say that, instead of at every point in time solving the differential equation to find out how I'm going to get there, what you could do is you could just say, well, take the path, take a probe path, a possible path, and evaluate this functional. And if you can modify the path so that the functional becomes minimal, or at least a stationary point, then that will automatically satisfy, that trajectory will automatically satisfy the differential equation. So variational calculus is basically just another way of doing the differential equations. They're mathematically, roughly speaking, they're equivalent. So any form of mechanics, you could ask, does it have a variational calculus formulation or not? Or can you put it into differential equations? So that's not the main question. Both Hamiltonian and Lagrangian can be put into functional form or variational form. The difference is really it may seem strange, but the difference really is about what kind of expansion of the space you're going to do. So in both cases, there's an extension of the configuration space to a doubled space. You introduce more coordinates. And the reason for that is because F equals ma is a second order equation. So if you want to take a second order equation and you want to make it into first order, you have to double the variables. So that's the same in Lagrangian and in Hamiltonian mechanics. The difference really is that in the Hamiltonian mechanics, you add momenta as your new coordinates, whereas in the Lagrangian formalism you don't. You add a slightly different quantity to double the space, and you could call those not momenta. You could call them velocities, or you could call them co-momenta. So they're kind of dual to each other. In the Hamiltonian formalism, you add the space of momenta, and that you could think of that, roughly speaking, as a vector space generated by the p's, the pi. But in the Lagrangian, you add the dual of that. Instead of the p's, you add the dual of the p's. So you work on the tangent bundle, whereas here you work on the cotangent bundle. So it seems like they're almost the same, right? That if we're going to increase our space, make a phase space by adding momenta, or if I add the dual of momenta, what's the difference? The difference is really that the Poisson bracket, when you pass it through this duality, it becomes very, very, very different type of object. You don't get a Poisson bracket on the other side. So that's why Lagrangian formulation of the theory it looks very different. It's not a question of dealing with brackets. It has a different type of structure. Yeah, I can tell that you want to know more about Lagrangian mechanics, but yeah, I'm not going to tell you about it. It requires more geometry background. Like the nice thing about Hamiltonian is that it's just a simple thing. If I just give you the bracket, and you can happily go away and compute any system. With the Lagrangian mechanics, I would have to develop a whole bunch of structures and explain how they are all related, and then there's a lot of differential geometry involved. So the Hamiltonian is definitely simpler. That's why I can that's why it's so easy for me to just tell you what it is. You can also look at there's this very famous book I think I put it on the webpage. There's a famous book by Arnold about the classical mechanics, geometric mechanics or something. Or there's this very famous book that is so heavy that you could use it as a weapon. It's the book by Marsden and Tromba, I guess, or not Marsden and Tromba. Marsden and Weinstein. They have a giant book on analytical mechanics, which explains the geometry of Hamiltonian and Lagrangian mechanics. And good luck to you if you want to read that book.
How do those compare with Landau and Lifshitz? Because like,
yeah, you could also look there, but the problem is that Arnold's book has has somewhat of the same problem, is that they don't make the mathematical substructure clear. They don't make it absolutely clear what the mathematical substructure actually is. They kind of put it all together. They provide it to you as one big package, but really what you would like to do is to chop it up into pieces and say, I start with a manifold that has no structure on it, then I put this piece of structure, and then you slowly build up the structure. That's not how they do it, because physicists don't know how to make definitions.
that's true.
But that's okay. Okay, we're coming to the end. Any other last questions? Let's see who's left here. There's only 6 people. Who's AN and who's NA? Both people who are invisible start with AN. Do you have video? Turn on your video. No, they refuse. Prefer not to use it. Okay, no problem. Is it the same person though? AN and NA? All right. Okay, everyone. Have a good rest of the week. I'll see you on Friday. Bye-bye.